Hello everybody, welcome to this tutorial. In this video we're going to talk about implementing your first CNN classifier. So first I used Google Colab because it's free and you can access to a GPU, or for example as you can see here, or you can select a TPU. Don't forget is if you use a TPU you should add some codes to identify your TPU. So I select the GPU and let's go ahead. First, you need to import your datasets. As you can see, TensorFlow, or for example, from cross.layers, we import convolutional layers, flatten, and other libraries. For example, to build our architecture. So let's see, and after that, we import our dataset, which is cifar10. We use cifar10 dataset for our project. It's a very famous dataset from cross libraries. We load that dataset and split that into train and test. So as you can see here, these are the train and test labels, and we change the type of the images from integer to float because we want to normalize and divide by 255. We normalize this dataset because it improves our optimization and training process, because for example when you have some grade levels between 0 and 255, they produce some large numbers and it makes it difficult for the training process. So we normalize the dataset, and after that we change the labels to categorical labels. That's one hot label, that specific class is 1 and the others are 0. So finally we use the categorical cross entropy for loss function, and pay attention to this point. So here we have our models, architecture. We use functional API. With this method you can easily connect your layers to each other, and I think it's a little more flexible than the sequential one. So here we have input layer. As you can see here, the shape is 32 by 32 by 3. 3 is the number of channels because the images are RGB. So we have the input layer, and after that we have a convolutional layer. We use conv2d for the convolutional layers. Here we have 20 filters, and the kernel size is 4 by 4. The stride is 2. Pay attention, when you use the stride more than 1, it reduces the size of the image. So here we have padding same, and we connect this layer to the input layer. After convolutional layer we use batch normalization. It reduces the internal coordinate shifts. That's very helpful. It accelerates the training process, and it prevents from vanishing gradients. So after batch normalization we have liquid for activation function. We use this hyperparameter 0.001, and we connect this layer to the previous one. We use dropout layer to prevent overfitting. We choose these hyperparameters to 0.2. It means that 20% of neurons will be disabled because the model will learn the features, the other features, and it prevents from overfitting. So after that we have convolutional layer again, like this layer, but here we have 30 filters and the kernel size is 30 by 3 by 3. And after that again we have batch normalization, liquid and dropout. And the third convolutional layer, here we have 40 filters. And after these convolutional layers we have flatten layers to flatten our data, and after flatten we use dense layer. Be careful when you use dense layer. You should flatten the data when you use, for example, convolutional architecture. you should flatten the data, and after that you can use the dense layer, as we can see here. The units, or for example the neurons, are 10. It's like the number of classes, so we have 10 classes, so we use 10 neurons. We use the activation function softmax for the dense layer, and we connect this to the previous one. So finally we build our model architecture. We select the input layer and the output layer, and we connect these layers using this code, and you can see the summary of your model with model.summary, and as you can see here, the number of parameters, the layers, and the activation function, and etc. is here, and you use the model summary. So after this, so here we have Adam for optimizing our model, and we select the running rate, as you can see here. So we compile the model, and using the optimization process like Adam algorithm, and the categorical cross entropy for loss function, and the metrics, as you can see here, is the accuracy, because we want to show the accuracy of the model and the accuracy of the training process. So for fitting our model, here we have the train data and train labels. We should select the batch size. You can, for example, use 64, 128, and other numbers. The epochs are 100. Be careful when, for example, use the batch size like 32. The train process is a little noisy, and you can play with these numbers, and you can watch the results. So after that, we shuffle the data after each epochs. It helps to prevent the model from learning the orders of the data. So here we choose the validation split. We choose the 20% of the training data set for validation. Be careful, don't use the test data set for tuning the model and tuning the hyperparameters, because you should just use the validation data set for evaluating your model and choosing hyperparameters. So after fitting our model, we want to show our results. As you can see here, for showing the loss of the model during training process, or the loss of validation data, or the accuracy of the train and the validation data, you can see here, and we want to use the history of the model for showing the results. So we plot that using pyplot library from matplotlib, and here we have the epochs and the accuracy. We label the graphs. So after showing our results, we want to evaluate our model using the test data and test labels. So here we want to show you some examples of how to see how the model can predict the images from test dataset. So we use these codes to predict the test data, and here we choose the 10 examples of test images, and we choose the randomly from the dataset to show you the prediction of our model. So we choose the size of the images to show, and we add the labels the bottom of the image to see the results of the prediction. So let's go to the results. So here we have the graph of our loss of the model. As you can see, it's a little noisy because our batch size is a little small. If, for example, you use 512, it will be a little more smoothly, and here we have the accuracy of our model. If the validation accuracy and the train accuracy for example, are differ from each other, our model is overfitted. Be careful to the results of the graph. So here you can see some examples. This one, the actual image label is deer and the prediction is deer. The actual label is automobile and the prediction is right. But for something here, for example, this one, the actual is frog, but the prediction is deer, and it's because as you can see, the train accuracy is about 70%, and the remain is the error of our model. Thank you for watching this video. Don't forget to subscribe if you use this video, and bye.